This is Neil with Anabit, and welcome to Making Accurate Ratiometric Measurements of Resistance Temperature Detectors, or RTDs. And that's exactly what we're going to talk about in this video. We're going to look at circuit configurations that use a current source, a high-resolution ADC, and a precision reference resistor to make highly accurate temperature measurements using RTD sensors. And these will be ratiometric measurements. And if you're not familiar with that term, we'll define that in the video. Before I get started, I'll just mention check out Anabit.co, where you can see our open source data converter products, as well as some of our blog tutorials. And of course, if you enter your email in at Anabit.co, you can get updates whenever we come out with new content or new products. Check us out on Instagram. And if you haven't subscribed already to our YouTube channel, please do. All right, let's get started. Okay, we have a lot to cover in this video, and here's an agenda, an overview of what we plan to cover. First, we're going to have a real quick introduction to what resistance temperature detectors, or RTDs, are. Then we're going to talk about how to make highly accurate ratiometric RTD measurements. And we're going to show the math behind what makes a measurement ratiometric and what its benefits are. Then we're going to dive more into circuit configurations, especially one for a 4-wire RTD. And then we'll look at a demo of that configuration in action so you can see how accurate it is. Then we'll also look at a 3-wire RTD configuration with this type of circuit. And then we'll close by looking at an example current source circuit. Current sources are key to this measurement we're going to talk about, or this measurement approach we're going to talk about. So we're going to look briefly at what a circuit for a current source looks like. Okay, resistance temperature detectors, or RTDs. These are sensors that allow us to make highly accurate temperature measurements over a large range. So when you look at an RTD sensor, they're typically going to have some letters and then a number for naming the sensor. And the letters correspond to the metal that's used in the sensor. So PT is platinum, Ni is nickel, Cu is copper. Platinum is by far the most common one out there. And then the number stands for what the resistance of that RTD sensor is at 0 degrees C. So PT100 you could see, PT1000, PT2000. By far, PT100 and PT1000 are the most common ones you'll see out there. Now, one thing to be aware of is when you make an RTD sensor measurement, the accuracy depends on multiple factors, right? First of all, we have the sensor itself. No sensor is perfect mechanically. So there's going to be some tolerance in the sensors. And so you have different classes of sensors. You have AA, A, B, C, and you can see the accuracies related to those type of sensors. Then there's the measurement hardware, right? That's what we're going to focus on in this tutorial, how to optimize the accuracy and resolution of your measurement hardware. You can do that so almost the measurement hardware is a very low contributor to the error of the measurement. And then there's the calculation method for taking that resistance reading and turning it into a temperature. Now for RTDs, when you're close to 0 degrees C, they're very linear. But as you go farther away, they become nonlinear, and that's where the calculation method is real critical. And no calculation method out there is perfect. The IEC-60751 is the most accurate, but it uses some pretty involved math. We will use that standard in our demo, but I'm not going to have a chance to go into it in detail, but there will be a link to the code that was used in the demo if you want to check that out. RTDs come in various different wire configurations. 2 is the least accurate because it doesn't account for wire resistance. 3 and 4 have ways to account for that, as we will see as we go through these circuit configurations. So here is a ratiometric measurement setup, and we'll go through the math here. But let's focus on the circuit diagram. So for simplicity, we just have a 2-wire RTD sensor, and we have our current source. That's what IDAC stands for, IDAC1. We have our high-resolution differential ADC, and then we have a reference resistance. This is a known resistor that we put into the circuit, precision resistor, that's going to create a voltage drop from the current source that the ADC is going to use as its voltage reference. And notice the reference input is also differential. Now, what's key here is that the current source goes through both the RTD resistance and the reference resistance. So any error in the current source is reflected on both the voltage drop for the RTD sensor and the reference resistor, right? So this is going to be key to the ratiometric aspect of this. So if we look at the left, we have the voltage drops across the 2 resistor elements. So we have the voltage for the RTD and the voltage for the reference resistor. And notice the resistances are different, but the IEXC, which is the excitation current, is the same for both. So if we plug those into the ADC's code expressions, and then we could change those voltages to the Ohm's law equivalent with I excitation times R RTD, and then below that I excitations times R ref times max code. We now have I excitation as a ratio on the top and bottom, and we know in algebra that means they can cancel out. So if you look at the ratiometric result, we can cancel out the current, and now the resulting code is a product of one resistance over the other times the max code. And if we rearrange that to turn it into what does the resistance of the RTD mean, it's the reference resistance times the code over the max code. The key point here is if there's any error in the current source, it gets canceled out because the error is reflected both on the RTD and on the ADC's reference. So that error is totally canceled out. So now our main error contributors are ADC errors that are not related to the reference, as well as any error in the reference resistance, right? So you want to get a precision reference resistance. And if you have something like a DMM or some way to calibrate it and measure it, you can even add accuracy even more to your measurement. Before I go on, I should mention a lot of what I'm covering here, I leveraged from TI or Texas Instruments application note, a basic guide for RTD measurements. I'll provide a link to it if you want to check it out in the video description. So I just want to make sure to credit them for that work. Let's talk about the 4-wire approach. So on the right, we have a very similar diagram to what you just saw, except instead of having 2 leads, we have 1, 2, 3, 4 leads. And we can see our current source. We can see in red the path the current takes. The key part here is the source leads, which is the leads that the current is flowing through, or the wires, are lead 1 and 4. The sense leads are lead 2 and 3. They're connected right against the RTD sensor, but they don't have current flowing through them, right? Now, technically, they have some current, very little, flowing into the ADC or programmable gain amp, depending if you're using an amplifier. But those are very high impedance inputs, so the current is very low, so we can almost just assume it's an open, right? And those resistors and capacitors they're showing there are just meant to be filters. So in a 4-wire configuration, we're able to cancel out the effects of the lead resistance because of the fact that we have lead 2 and lead 3 serving as our sense leads. Then, of course, you can see the current path goes through our reference resistor to ground. So it's the same setup we had before, but it was 2 wires where we were not canceling out the resistance of the wiring. But here we can. And then we also added that programmable gain amp. Sometimes you might find an ADC that has a programmable gain amp built in, or you can add an external one, an instrumentation amp, or you might not need one depending on your setup. Now, one of the reasons, though, you might want an amplifier is for your current source, you could choose a high current value, right? A high current value creates a higher voltage drop, which makes it easier to measure with the ADC. But higher value current sources eat up more power. But more importantly, higher current is going to cause your sensor to heat up, self-heating, right? So when you heat a material up, its resistance increases. So if we put too much current through the RTD, we're going to cause it to read a too high of a temperature due to self-heating of the current source. So there's a balance. We want to have a high enough current where we're not in the noise or noise doesn't affect our measurement, but we want to have a low enough current to avoid self-heating. And the lower your resistance of your RTD, for instance, we're using an RTD that's only 100 ohms, the more susceptible you are to self-heating. So that's a key point that you want to keep in mind. And it's important for the RTD sensor as well as the reference resistor. So often people want to use lower currents and then they'll use an amplifier to boost that level up to get a higher resolution because you're increasing the amplitude of that signal with the amplifier. Now, if we go to the math is basically the same as what we just went through, except we added in the gain factor. If you're not using an amplifier, then you can just take that out. But I wanted to show that with the gain factor in there to get an accurate resistance measurement. Okay, So let's talk about how you might set some of the parameters, right? Because there's a lot of different parameters you want to set and you want to maximize them for accuracy and for the range of the ADC based on what you're using. So these are the parameters we're going to use for the demo I'm about to show. And for the demo, I'm using Anabit's Precision Logger open source reference design. It has a 32-bit ADC on it, so very high resolution. It has a built-in programmable gain amp, and it also has two low current sources that we can use. So it has a lot of the elements for making this measurement. Let's set the range that we want to measure for our RTD sensor. So PT100s, they can go up as high as 800 degrees C, but they get very expensive when they go up that high. And for our application, we're just going to say we need it for negative 200 C to 500 C. And when we look at that range, we want to know what are the resistance values from the two ends of the ranges, because we want to know what our maximum voltage drop is going to be. So we can see at 500 C, it's going to be about 281 ohms. And since we have a 32-bit ADC, but that ADC returns a sign value, so we take one of those bits out and we do 2 to the 31 minus 1 to account for 0, and that's our max code that we could get from the ADC. Then this board is configured with a negative to plus 2.5 volt power supply, so that's essentially the range of the ADC and the programmable gain amp. Of course, we don't want to go all the way up to 2.5 because then you start to saturate that amplifier. So you want to kind of stay within a margin of that voltage range. For our reference resistor, we're using a 1 kilo ohm precision resistor. And then for the current source, we're going to go with 250 microamps. And then let's check what our voltage range is, because that's going to tell us what we can set our gain for the programmable gain amp. So the voltage reference drop across the reference resistor is going to be about 250 millivolts. For the RTD, at the max temperature is going to be 61.8 millivolts. We could actually do a gain of about 4 and still be below 250 millivolts, right? And I say that because we have to be below our reference voltage. If we go above our reference voltage, we'll saturate the ADC. So we're going to do a programmable gain amp setting of 4. All right, so let's look at this configuration with these parameters in action. And what we're going to do for our demo is we want to compare the ratiometric approach with a non-ratiometric approach. So I'm going to use virtually the same setup. We're going to do a ratiometric version, and then in the demo, I'm going to show a version where I use the same current source, same setting, but instead of using the ratiometric resistor to create the voltage reference, I'm going to use another voltage reference that's not related to the current source. Okay, here's a zoomed in picture of our precision logger board. We have our 4-wire RTD set up here. This outer wire is where the current source goes into, and this is where the current source comes out of. And I don't know if you can see it, but I have my precision 1K ohm resistor soldered across these two leads. And then this white wire serves as the return path to ground for the current source. So for our first configuration, the ratiometric configuration, let's see what we get with our measurement. So I'm going to zoom in so you can kind of see that closely. I'm just using the classic Arduino Uno with SPI communication to communicate. Here I have 2 temperature sensors in water. So what I'm doing is I wanted to have a reference measurement so you can kind of see that this is accurate. And so I'm using a 5 kilo ohm thermistor sensor with a highly accurate DMM that's measuring it. So you can see that I'm making the measurement in C. The reason I put the probes in water is because the resolution is so sensitive that, like, if I were to breathe and my breath hits one or the other, the temperatures go off in different directions. So the water helps stabilize the temperatures, but that's what type of resolution we're getting. So that's going to serve as the reference. Now, as I do this demo, you're going to notice the temperature is going to slowly go up, because I got cold water, and the cold water is slowly heating up, which another thing shows how great resolution we're getting in this demo. So we can see the temperature slowly going up. And here I'm printing out the measurements to the serial monitor. I'm going to refresh them. And you can see here, we're printing out the resistance and the temperature in C, and we can see they're slowly creeping up, and they're very close. So now what I'm doing is I cut this out of the video, but basically what I did was I switched that wire for the current source because we don't want it going through the reference resistor for the non-ratiometric demo. So that's what we're doing. And then what I did is I changed a variable in my code from true to false to say that I'm not doing the ratiometric measurement this time. So I'm going to reset the interface, and now we're doing the non-ratiometric measurement. And we can see we have a much different result. We're only getting 5.8 degrees. And so remember, this value is basically the same as the RTD sensor, right? It was only maybe 20 milli different, and now we're like 2.5 degrees difference. So, and that's due to what? That's due to error in the current source and the voltage reference, right? So when we did the ratiometric approach, those two, that the error came from just the current source and it canceled out. Now we have those two different errors, and if we wanted to make this more accurate using a non-ratiometric approach, we would probably have to measure our voltage reference, measure our current source, and calibrate them in software, have a correction factor to get better accuracy. Okay, we just looked at the power of a ratiometric measurement as far as accuracy and resolution. Now we're going to look at a 3-wire configuration, right? So this isn't too much different than what we just saw. The only difference is we have 3 leads instead of 4, right? So the current is flowing through one of our leads. So that resistance is going to be counted in this first measurement, AN1 and AN2. Actually, I should say the lead 1's resistance is going to be counted in that measurement. So what we do here is we do 2 measurements, right? And there's more than one way you can do this, but one way you could do it is you first make the load, the AN1 and AN2 measurement, then you make AN2 to AN3 measurement, and that represents the resistance of lead 3. And if we assume that lead 3 and lead 1 are both the same length, so they're both the same resistance, we take that second measurement of resistance and subtract it from the first, which should leave us just the RTD measurement. The measurement from lead 2 to lead 3 is going to be very low, so that might be a measurement where you up the gain of your programmable gain amp even more. So the downside to this approach is you do have to make 2 measurements, so it leads to a longer measurement time. Now, Anabit has another RTD measurement video, especially for 3-wire measurements, that uses what's known as a Wheatstone bridge. Wheatstone bridge adds a little more complexity to your circuit because you need some more precision resistors, but it allows you to do a ratiometric measurement with just one measurement. So if you didn't want to do it with this approach, or you didn't want to use a current source, there's another way to do it, and I'll have a link to that video in this video description. But this will return a very accurate 3-wire measurement as well. I'm just going to comment on this briefly, but I'm leveraging this image from a video from the Forcetronics YouTube channel. And it was a video done years ago, and I'll put a link to it in the video description, but it talks about 2 different ways to design a current source circuit. In this image, we have an Arduino, but really I'm using the DAC output on the Arduino, and it's driving the non-inverting input of an op-amp. Then we have the inverting end of the op-amp connected to the top of a sense resistor, right? That's then connected to ground. And then that op-amp is driving the gate of a MOSFET, N-channel low-side MOSFET. And then you have VCC, which is some power source, and then we have the load. So if we relate this to the RTD diagrams we just saw, the load would be the RTD sensor and the reference resistor, right? So this would be below this in the path to ground. And the way this works is the DAC output setting, you set it to some voltage level, and the op-amp will drive the MOSFET so that that same voltage level appears at the sense resistor, right? Essentially creating an equilibrium at the op-amp's input. So as an example, let's say we set the sense resistor to 1 kilo ohm, right? If we put 1 volt into the non-inverting input, the op-amp will drive the MOSFET to get a 1 volt drop across the sense resistor, which in turn would equal 1 milliamp voltage, 1 milliamp of current flowing through the sense resistor. Okay, that's it for making an accurate ratiometric measurements of resistance temperature detectors. If you have any questions from the video, please use the comment section below. And if you think I missed anything or have anything to add, please do the same thing as well, and check out anabit.co. Thank you for watching.